All right, welcome Calc BC students. We're going to start covering the next section, which is parametric equations, which is covered in section 10.2 and 10.3. One thing to point out is that there's a lot of stuff with parametric equations dealing with physics that's not covered explicitly in your textbook. So there's only really a small portion that's covered in your textbook. So please watch these videos to make sure you get everything you need. Okay, so what are parametric equations? Probably the best way to start this off is let's go back to physics and look at a projectile motion problem. So let's say we have somebody kicking a soccer ball. It's a terrible drawing. And the soccer ball is put into projectile motion. And this is kicked at some initial speed, which is the magnitude of velocity, v naught, and at some angle theta. Okay, so if I actually plot this path, and this is something we didn't do in physics. I mean, I guess it's something we could have done, but it's not something typically that's done there. But if we plot y versus x, then we're going to get this parabolic path in y and x. And we actually have here a function that's y is equal to a function of x. Now, we're mainly concerned in physics with looking at x and y in terms of time, not y as a function of x. So that's kind of where something new is going to come in this particular section. All right, so if we look at our equations for this projectile motion, we know that x is a function of time is equal to v sub x, the x component of velocity, which would be the speed, the initial speed, times cosine of theta, times the time at any given point. And we also have y as a function of time, which is equal to minus 1/2 g times time squared plus v y naught times t plus y naught. And so here we have these equations in time, but we don't really have y as a function of x. So just to make this a little bit simpler, I'm going to put this x and y in just terms of some numbers. So let's say that x is a function of time. And let's say my x component of velocity is 3 meters per second. So that's 3 times the time, and that time is a variable. And in the y direction, let's put some numbers in. So y as a function of time is equal to minus g. Well, g is 9.8 meters per second squared, so I'm just going to kind of round up just for this mathematics example. So let's say this is minus 5t squared, plus let's say the initial velocity is, in the y direction, is 7 meters per second, times time, and y naught is 0. Okay, so if we want to communicate these two in what's called parametric form, what we're going to do is just communicate it as x is a function of time, comma, y is a function of time. And it's kind of held with these kind of like triangular brackets. And so we'll say this is equal to bracket the x value of position, which is 3t, comma the y value of position, which is minus 5t squared, plus 7t. And so this is a way of communicating our position vector, and this would be in units of meters, and for time is greater or equal to 0. So this is our position vector in parametric form. Now, the first thing we want to do in this parametric chapter is get this into a rectangular equation. And to get this into a rectangular equation, which is y is equal to a function of x, so this is something new. The first step in doing this, step 1, is I want to solve for time in the x position equation. So what I'm going to do is I'm going to look up at the x position, which is 3t, and so I've got x is equal to 3t. And I'm going to solve this for time, and so time t is going to be equal to x over 3. Okay, and then step 2 is I'm going to put this t, this time, into the position equation in the y direction. Now, note that the y direction is initially a function of time. So the y position as a function of time is going to be equal to minus 5t squared plus 7t. So what I'm going to do now is I'm going to take my time value that I calculated in the x direction. So time is equal to x over 3, and I'm going to put that in for all of the times over here. And if I do so, then I get y as a function of x is equal to minus 5 times t squared. So t is quantity x divided by 3, quantity squared, plus 7 times t, and t is x over 3. Okay, and so so now I've got y as just a function of x instead of time, which will enable me to actually graph the path of this projectile. All right, so I'm going to go ahead and rewrite that up here. And so I'm going to go ahead and square that out and rewrite. So I've got my y as a function of x now is minus 5/9 x squared plus 7/3 times x. So now I've taken the position equations as a function of time in x and y and have related them both together through time to get y as a function of x. And so this enables me to actually plot out the path of this particular projectile. And so if I graph the y position versus the x position, then the path of the projectile is going to look like something like this. And this path is described by this y is equal to minus 5/9 x squared plus 7/3 x. Now, there's a couple cool things we can do with this at this point. One of them is we can find an equation for the tangent line slope at any point on this curve. So this tangent line slope is going to be the slope of the tangent line here is going to be equal to dy dx. So I can just go up to my equation here for y and take the derivative. And if I do so, so I got this program working. So then the derivative of y as a function of x is just differentiate it normally. So it'd be minus 5/9 x squared. So the derivative is going to be 2x. That's going to be minus 10/9 x plus 7/3. And by taking the derivative, this gives me the tangent line at any point along the x, along with the x values, and then this will enable me to determine whether a function is increasing or decreasing at a certain x value. It can also be helpful in finding horizontal tangent lines, the location in x, etc. So this can do anything the first derivative can do normally. And then I can also take the second derivative, and the second derivative of this particular function, d squared y dx squared, in this case is just equal to minus 10/9. And this gives me the concavity of the graph y and x. And it can also help me test for extrema if I find the critical points using the first derivative. I could use the second derivative to test to see if I've got a relative min or a relative max. So in this particular case, the second derivative is negative, which tells me that the graph is concave down the entire way. And if I were to set the first derivative equal to 0, I could find the critical points and figure out at what x value this critical point is. And then the second derivative test would tell me that that was a relative max. Another interesting thing we can do with y as a function of x is we can determine the arc length of the curve, which is really the distance along the path of the projectile. So this is the distance traveled by the object. So that's the distance of this entire path here. And this is something we couldn't do in physics. And so if you recall from chapter 7, we do have an equation for arc length. And so the arc length, which is the distance traveled along the path, would be the integral from the initial x value to the final x value of the square root of 1 plus the derivative, which is dy dx, quantity squared dx. And again, this is the equation from arc length that we learned in chapter 7. Now, if we wanted to apply this to the above example, it's actually a little bit tricky. One of the tricky things is try to figure out what this later x value is, because I know the initial x value in this particular case is 0, but to solve for the final x value, I would have to actually go up to my equation for y as a function of x and find the two zeros for y. And as you can see, you could factor out an x, and one of them is 0. And then you could solve for the other value of x down here. And so that causes this to be a little bit tricky. And it's actually not very efficient for most physics problems. And so although it's useful in some cases, going back to our first page, to get these parametric equations where you have x and t and y of t into a single function as y is a function of x, it's not terribly practical from a physics standpoint. And so in the next video, I'm going to show you what an easier way to do this and really a more practical way of doing this. All right, so I'll see you in the next video.